Welcome, curious minds, to another expedition into the core of what truly matters in our rapidly evolving technological landscape. Today, on the deep dive, we're embarking on a really crucial journey into the intricate world of AI security. And we're drawing insights from one of the most comprehensive guides available. Okay, let's unpack this. Our guiding star for this deep dive is an incredible resource, the ISACA AAM Official Review Manual. Now, when we say manual, don't picture some dry, dusty textbook. Seriously, think of it more like a comprehensive, living guide. It's meticulously crafted for anyone who's serious about understanding the real intricacies of AI security management. Yeah, and this isn't just about passing a certification exam, although it helps with that too. It's truly about gaining practical, actionable knowledge, stuff you can apply right now to build and maintain secure AI systems. And for those maybe less familiar, ISACA isn't just any organization. They're a global association, and they've championed trust in technology for, over 55 years now.
That's right, a long time. And they have this vast network, over 185,000 members and experts worldwide. They really are at the absolute forefront of emerging tech like AI.
Exactly. Their commitment to education, training, global workforce development in areas like info security, governance, assurance, it's really unparalleled. So this manual, it represents a comprehensive collection of, information and experience, all distilled down to help you navigate the complexities of AI security. It's essentially like getting a condensed masterclass.
What's truly fascinating here, I think, is how thoughtfully this manual is structured. It's not just a random collection of topics sort of thrown together, not at all. It's designed to be a profoundly practical resource. It covers 3 core domains, which, collectively they form the bedrock for anyone interacting with AI or even just trying to understand it better.
Okay, so what are those domains?
Well, first, you've got AI governance and program management. That's a substantial chunk, about 31% of the material. Then there's AI risk and opportunity management, also 31%. And finally, technologies and controls. That's the biggest domain, at a significant 38% of the content. And Chapter 3, which is our focus today, dives right into that critical third domain. Which makes it absolutely crucial for practical application, in the real world. It really grounds the theoretical stuff in something tangible. So the point is, even if you're not currently prepping for a certification exam, understanding this structured, kind of holistic approach to AI security is incredibly valuable.
Definitely.
The way AI is evolving so rapidly means constant learning. And a framework like this, it's not just about rote memorization. It helps you gain that knowledge quickly, but also thoroughly. It's designed, I think, to provide those aha moments, without feeling completely overloaded with information. It helps you grasp how all these vital concepts are interconnected.
Right.
It moves beyond just the definitions, the theory, to show you precisely how these pieces fit together to build secure, trustworthy AI systems in a tangible, actionable way.
Absolutely. And that structured approach is exactly what we're leaning into today. We're going to guide you through some specific critical sections of this manual. We want to extract the most important nuggets of knowledge, the things that often get overlooked in just general chats about AI. We're zeroing in on Chapter 3, which is meticulously titled Security Controls and Monitoring. Now, interestingly, while the manual typically starts chapters with a kind of foundational overview, our source material here, it just jumps right into the deep technical content of Part A, AI Security Architecture and Design. Yeah, so we're diving straight into the architectural blueprints, you could say, before we even get to the specific controls themselves. So what does this all mean for our deep dive today?
Well, when we talk about AI security, before we can even think about where to put a firewall or how to monitor for anomalies, we first need a really crystal clear understanding of what AI is at its core, and maybe more importantly, how it's fundamentally built.
Right, the foundation.
Exactly. This section lays that groundwork. It gives us the essential vocabulary, the conceptual blueprint. It's that critical first step, like understanding the structure of a building before you design its alarm system, right?
Indeed. Section 3.1 really begins by laying out the architecture of AI, a multidisciplinary foundation. And this is crucial because AI, at its very essence, it isn't just a subfield of computer science. That's a common misconception.
Yeah, people tend to think that. It's actually this fascinating, quite intricate integration of diverse academic and practical fields. Computer science, yes, naturally, but also mathematics, engineering, and even aspects of psychology play a role. The overarching goal here is to develop intelligent machines. Machines that can reason, solve complex problems, perceive the world around them, and crucially, make autonomous decisions.
And that's a big shift from traditional software, isn't it?
Oh, a profound paradigm shift. Traditional software engineering, you painstakingly write out every single explicit instruction the program follows. With AI, the machines are designed to learn and, in essence, make their own choices, often in ways we didn't explicitly program them to. So within this broad definition, the manual first introduces us to machine learning, or ML. This is essentially a fundamental subset of AI.
Okay.
It's where algorithms learn and adapt from data without being explicitly programmed for every single conceivable scenario. Think of it less like giving a kid a strict rule book for every situation, and more like letting them learn from experience, recognizing patterns, making predictions based on the data they've seen.
Makes sense.
And in the realm of security management, ML is absolutely vital. It underpins sophisticated threat detection systems, for example, enabling them to identify these subtle patterns of malicious activity that would be, frankly, impossible to catch with predefined static rules.
Like zero-day attacks.
Exactly. Detecting zero-day exploits or advanced persistent threats often relies heavily on ML models learning what normal network traffic looks like and then flagging anything that deviates, any anomaly. But, and this is important, this also introduces unique security challenges. Things like adversarial attacks.
Ah, yes. Heard about those.
Right, where an attacker subtly manipulates the input data just enough to fool the ML model, maybe making it misclassify malicious activity as benign. It's a constant cat-and-mouse game.
Okay, so that's ML. What comes next?
Well, building on ML, we then delve into deep learning, or DL. This is positioned as a subset of machine learning, but it specifically uses these multi-layered neural networks. These networks are designed to extract increasingly hierarchical features from raw input data. You can almost visualize it like peeling back the layers of an onion.
Okay.
Each successive layer of the neural network understands increasingly complex and abstract features. This is the tech that's driven so many of the recent breakthroughs we've seen. Highly accurate image recognition, sophisticated speech processing, truly natural language processing.
The stuff that feels almost like magic sometimes.
It can seem that way, enabling machines to truly see, hear, and understand in ways that, were once purely science fiction.
So, security implications for deep learning.
Well, DL offers incredible capabilities for detecting complex threats, say in visual data like security camera feeds or auditory data, but its black box nature can be a challenge.
Meaning we don't always know why it made a decision.
Precisely. It can be difficult to fully interpret why a DL model made a specific decision, and that can pose real challenges for incident response, for forensic analysis. If you don't know why it flagged something or missed something, it's harder to fix or trust.
Right, I see. That makes sense.
And then there's generative AI, or Gen AI. This has really captured the public imagination recently, hasn't it?
Oh, absolutely. It feels like it's everywhere.
It often becomes synonymous with AI for many people. Gen AI has this remarkable ability to create new, original content, whether that's coherent text, realistic images, functional computer code, even expressive audio. How does it do that? By learning intricate patterns and structures from vast amounts of training data. It's being used really innovatively across industries: marketing copy, social media content, assisting with complex problem solving, even designing new materials.
There's a dark side too, right?
Definitely. As the manual points out, we have to critically acknowledge its significant potential for misuse. From a security standpoint, this means things like the creation of highly convincing deepfakes or sophisticated misinformation campaigns used in social engineering attacks.
And generating malware.
Yes, or highly convincing phishing emails that can evade traditional defenses, polymorphic malware that changes itself. This capability introduces entirely new attack vectors and really necessitates a rethinking of our defensive strategies.
It's a whole new ballgame.
It really is. Looking further out, the manual also touches on concepts that are, well, maybe more theoretical now, but rapidly moving towards reality. Artificial general intelligence, AGI, and super AI.
AGI, that's the human-level intelligence idea.
Exactly. AGI aims for AI systems to possess human-level cognitive abilities across multiple diverse domains. Not just being good at one thing, like chess, but being able to apply intelligence flexibly. Sensory perception, fine motor skills, emotional intelligence, natural language, real versatility.
And super AI.
That's the hypothetical future state, where AI wouldn't just equal, but would fundamentally exceed human intellectual capabilities in virtually every field.
Wow.
Yeah. The concept suggests unprecedented creativity, groundbreaking innovation, novel solutions we can barely conceive of today. And naturally, this immediately raises incredibly profound questions about future security implications.
You mean securing something smarter than us?
Essentially, yes. Imagine the challenge of securing systems that can autonomously generate new attack methods faster than humans can possibly respond. It's a mind-bending prospect.
Definitely food for thought. You mentioned generative models earlier.
Ah, yes.
Yeah.
Digging a bit deeper into the generative side, the manual elaborates on specific generative models. It gives examples like generative adversarial networks, or GANs, and also general purpose models like DALE and GPT that people might know.
GANs. How do they work again?
They're particularly clever. They involve this dynamic competition between two distinct neural networks. You have a generator that creates new content and a discriminator that tries to figure out if the content is real or fake.
So they battle it out.
Exactly. They compete in this continuous feedback loop. The generator gets better at fooling the discriminator, and the discriminator gets better at spotting fakes, until the generator can produce outputs that are virtually indistinguishable from genuine data.
Fascinating.
And DALE and GPT are well-known examples using similar principles, creating everything from original art to detailed prose. But from a security angle, GINs can be used by attackers to generate highly convincing phishing pages, synthetic identities, making traditional detection much harder.
Okay. And all these different AI types rely on different ways of learning.
That's right. The manual highlights the different types of learning that fundamentally underpin these systems, and each has its own security considerations. First, there's supervised learning. This is probably the most common one.
Supervise it like having a teacher.
Pretty much. Models learn from extensively labeled data to predict outcomes. You provide the model with inputs and the correct outputs, and it learns the mapping between them. So, for example, in regression, it learns from historical data to predict continuous values, like forecasting house prices based on features like square footage, location, etc.
Right.
In classification, the model learns to assign data points to discrete categories, like identifying spam emails, spam or not spam, or assessing credit risk, high risk or low risk.
And the security risk there.
Often revolves around the training data itself. If the labels are inaccurate or worse, maliciously poisoned by an attacker.
So the model learns the wrong thing.
Precisely. It learns incorrect associations. That could lead to misclassifications, maybe allowing threats to bypass defenses, or flagging legitimate users incorrectly. Data integrity is key.
Okay, that's supervised. What else?
Then there's unsupervised learning. This is quite different and arguably more complex to secure in some ways. Here, models learn from unlabeled data. They have to find hidden patterns, structures, relationships without any explicit guidance. No correct answers provided.
Learning by observation, then.
Exactly. Like discovering inherent order within chaos. Clustering is a prime example. The model groups similar data points together based on their intrinsic characteristics without being told what defines a group.
How's that used in security?
Widely used in network security, for instance, identifying distinct groups of user behavior or network traffic patterns, which can then help flag unusual patterns that don't fit any known group. Other unsupervised techniques include association rules, finding statistical links like IP address A often talks to IP address B just before an attack. Dimensionality reduction simplifies complex data useful for security log analysis. And anomaly detection is absolutely crucial.
Spotting the weird stuff.
Basically, yes, identifying deviations from normal behavior. It's a cornerstone of many advanced cybersecurity systems trying to detect unusual activities that might signal an intrusion.
But the challenge is new attacks.
Exactly. The novelty of attacks.
Yeah.
If the system has never seen a particular anomaly before, how does it classify it accurately? And how do you stop an attacker from generating malicious data that looks normal to evade detection? Big challenges there.
Okay, one more type of learning.
Yes, reinforcement learning, RL. This involves an agent, the AI learning through trial and error interactions within an environment. The agent performs actions, gets feedback rewards or penalties, and then adjusts its strategy over time to maximize its cumulative reward.
Like training a dog with treats.
That's a great analogy. Positive reinforcement. Good behavior gets rewarded. It's exceptionally powerful for tasks requiring real-time decisions in dynamic, uncertain situations. Think robotic path planning or enhancing autonomous driving systems.
And in security.
It's gaining traction for optimizing defensive strategies in highly dynamic threat environments. Learning to adapt to new attacks, evolving adversary tactics in real time. But securing the RL agent itself is an emerging field. Could attackers manipulate the rewards to teach it insecure behaviors?
Wow, lots to consider. And all these learning types use neural networks.
Often, yes. They're frequently implemented through neural networks, NNs. These are sophisticated algorithms, inspired, as you said, by the structure and function of the human brain. designed to recognize intricate patterns and make complex decisions. They consist of these interconnected nodes or neurons organized into distinct layers. You have an input layer receiving the raw data, then one or more hidden layers where the real processing happens, complex mathematical transformations, nonlinear activations. That's where the thinking or feature extraction occurs.
And finally,
An output layer that produces the final result, a prediction, a classification, whatever the task is.
are there different kinds of neural networks?
Oh yes, several common types. Feed-forward NNs are the simplest data flows one way, input to hidden to output. No loops. Good for straightforward image classification or text recognition. Then you have recurrent NNs, RNNs. These are designed for sequential data, like language or time series. They have an internal memory, allowing them to remember previous inputs in the sequence. Excellent for language translation or speech generation.
Okay.
And finally, convolutional NNs, CNNs, are highly specialized for grid-like data, especially images. They excel at image processing, object detection, medical imaging, by automatically learning spatial hierarchies of features.
And each has its own security quirks.
Absolutely. Even susceptibility to specific adversarial attacks tailored to their structure. Understanding these architectural nuances is critical for designing effective security controls.
Here's where it gets really interesting, I think. Because these foundational concepts we've just discussed, the learning types, the network architectures, they aren't just academic. They directly translate into the AI systems we use, we interact with every single day. Which brings us neatly to section 3.1.7 in the manual, AI considerations. This delves into some more familiar terms you've probably heard bandied about, but now we can understand them with a deeper appreciation of their mechanics and, crucially, their security implications.
Right, connecting the theory to practice.
Exactly. First up, the big one. Large language models, or LLMs. These are, they're colossal AI systems, not just algorithms, trained on absolutely massive amounts of text data, often petabytes from the whole internet. Their purpose: to process and generate human-like language with just astonishing fluency. Makes them incredibly versatile.
Incredibly.
Think content creation, drafting marketing copy, technical docs, summarizing legal documents, instant translation. They've truly transformed how we interact with information.
No question.
But security-wise, the sheer volume of training data means potential exposure to sensitive info, right? And their generative power opens doors for sophisticated phishing, spreading convincing misinformation at scale.
Absolutely. Data privacy during training and preventing malicious use of the output are huge concerns.
And directly related to LLMs and any generative AI are prompts. Simple idea, right? The instructions or inputs you give the AI.
Seems simple, but it's critical.
It really is. Prompts directly guide the output, influencing accuracy, relevance, even the tone. This is a skill now, prompt engineering. Just focused on crafting effective inputs to get the best results, learning to speak the AI's language.
It's becoming a real art and science.
But from a security view, there's also prompt injection, isn't there?
Yes, a significant threat. That's where malicious instructions hidden within a prompt try to bypass the AI's safety guidelines. It could lead to data leakage, unauthorized actions, generating harmful content. It's like finding a backdoor through clever wording.
Sneaky. Okay, next up, foundation models. What are these?
Think of them as large, general-purpose AI models, trained on incredibly broad, diverse data sets. That makes them powerful and versatile. What makes them foundational is that they can be adapted or fine-tuned for a wide variety of specific downstream tasks, often with relatively little extra training data needed.
They're like a base layer.
Exactly. A robust base for countless specialized AI applications. Instead of building every AI from scratch, you start with a foundation model and tailor it. Very efficient.
But the security risk is concentration, maybe.
Precisely. A single vulnerability in a widely used foundation model could potentially propagate across thousands of applications built upon it. Creates a massive single point of failure for an entire ecosystem. Securing these is paramount.
Makes sense. Okay, Transformers. Not the movie robots, I assume.
Chuckles. No, not those. Transformers refer to a specific, quite groundbreaking type of neural network architecture. They've really revolutionized natural language processing, NLP. They're renowned for their efficiency and effectiveness in handling context and relationships within sequential data, like sentences or paragraphs. Unlike older architectures, they can process all parts of a sequence in parallel.
Faster and better at understanding context.
Essentially, yes. especially long-range dependencies in language. They've massively improved how AI understands the nuances of human language, allowing for much more sophisticated interactions.
Security angle.
Understanding their internal workings, particularly their attention mechanisms, is key to defending against adversarial attacks that try to exploit those mechanisms to manipulate the output.
Got it. Which brings us nicely to natural language processing, or NLP itself.
Right. NLP is the broad field of AI focused on enabling computers to understand, interpret, and generate human language.
Like voice assistants, sentiment analysis.
Exactly. Your smartphone understanding voice commands, tools gauging public opinion from social media, text analysis extracting insights from legal documents or customer feedback. It's all NLP. Bridging the gap between unstructured human communication and structured computer understanding.
And in cybersecurity.
Critical for analyzing security reports, understanding phishing email content, generating threat intelligence. But it also opens avenues for attacks that exploit language nuances like ambiguity or sarcasm to fool NLP-based security tools. If we connect all of this to the bigger picture, it becomes abundantly clear. These individual components, the learning types, the architectures like transformers, the applications like LLMs, they don't exist in a vacuum.
They all build on each other.
Intricately layered, often interacting in complex, synergistic ways, creating the sophisticated AI systems we now see everywhere. Understanding these layers, how they fit together, including their inherent dependencies and vulnerabilities, that is the absolute first critical step to effectively securing them.
You can't protect what you don't understand.
Exactly. You simply cannot. And for AI, that understanding goes way beyond just knowing what it does. It means understanding how it does it and what its fundamental dependencies are, right down to the foundations.
Okay, let's unpack this further then. So you've got a solid grasp now, hopefully, of what AI is, its foundations, the components, the learning types. The natural and, frankly, absolute critical next question is, how do we make sure these incredibly powerful systems are secure by design?
Yes. That's the crux of it.
This isn't about patching things up later, is it? Or adding security as some kind of afterthought. It's about embedding security from the very first thought, the initial concept, the design phase. Which brings us squarely to 3.2 architecture considerations in the manual.
Precisely. And the core idea here is 3.2.1 AI security by design. This isn't just, a nice-to-have best practice. It is absolutely paramount for AI systems. It represents a proactive approach, not reactive, ensuring AI systems are built with robust protections against threats and vulnerabilities throughout their entire life cycle.
Not just bolted on at the end.
Exactly. Instead of trying to retrofit security after development, which is often ineffective, costly, and can even introduce more vulnerabilities, we're talking about integrating security right from the initial design. Meticulously threading it through development, testing, deployment, and ongoing operation. Baking in resilience, trustworthiness, ethical considerations from the very foundation.
How do you actually do that in practice?
Well, a key part of achieving this security by design for AI is through infusing AI across the DevSecOps continuum.
DevSecOps, integrating development, security, and operations, right?
Correct. It's a modern software development approach focused on a continuous automated process. For AI security, this means weaving security activities and considerations into each and every stage of this cycle, recognizing the unique challenges AI introduces. Let's break down what that looks like. Starting with the plan phase. This is requirements gathering, strategic vision, initial design. Here, AI security means meticulous threat modeling.
But specifically for AI threats.
Yes. Identifying risks not just to the code, but to the data, the model itself, think adversarial attacks, model poisoning, and the outputs. This also means defining clear security policies and, very importantly, developing ethical AI policies right from the start. You're anticipating potential harms, malicious actors, unintended biases, and building safeguards into the project's fabric before a line of code is written or data collected. Addressing vulnerabilities here is far cheaper.
Makes sense. Then comes code.
Right, the actual development of models and infrastructure. Secure architecture design is vital. Developers use static code analysis tools to find vulnerabilities early. For AI, this might include analyzing model architectures for known weaknesses. Machine learning can even assist code reviews, finding issues maybe faster than humans alone. Vulnerability checks for the code, but also for all the libraries and frameworks the AI depends on, are crucial. And fostering a collaborative culture where security is everyone's job helps catch things early, building secure components from the start.
And the build phase, putting it all together.
Exactly. Integrating components, compiling, preparing for testing. This needs effective change request management. ML can even assist here, maybe identifying anomalies in the build pipeline itself, an unexpected dependency change, for example. This is also where you do rigorous vulnerability assessments on the compiled artifacts and initial ethical bias identification, making sure security configurations are right as it's assembled, flagging biases before they become systemic. Automated checks are critical here.
Followed by test. This must be huge for AI.
It is. Rigorous verification and validation. Meticulous data quality checks ensuring the AI learns from clean, representative, secure data. Then security testing, adversarial testing to probe the model's resilience. Precise version management for models and datasets is crucial for rollbacks. Automated tools for penetration testing, fuzzing, security regression tests are essential. Formal approval processes for changes. Continuous vulnerability assessments. The goal isn't just does it work, but does it work securely under stress and attack?
Okay, then deploy, getting it out there safely.
Right. Secure release and integration into production. Final model validation before release. Robust, automated release pipelines and deployment processes to minimize human error and configuration drift. You can even use AI anomaly detection to monitor the deployment process itself for anything unusual, safely introducing the AI into the operational landscape.
And finally, operate, keeping it secure once it's live.
Yes, continuous monitoring and maintenance. Here, AI itself can enhance security. Advanced anomaly detection in real time, data leakage prevention, automated root cause analysis for incidents. This is where AIOps AI for IT operations really shines. Correlating events, predicting issues, automating responses. And this whole DevSecOps continuum for AI, it's cyclical.
Learning from operations feeds back into planning.
Exactly. New attack patterns, model drift, that insight feeds right back into planning and coding. It's adaptive, resilient security throughout the AI's entire lifespan. Design security in, then constantly verify, adapt, and improve.
Here's where it gets really interesting, though, because, okay, we can build the most secure AI system, perfect architecture, infuse security everywhere in DevSecOps. But if the data underpinning it isn't right, or if it changes unexpectedly,
then the whole sophisticated structure can potentially fall apart, yes.
which highlights the absolutely crucial role of 3.2.2 data dependency within AI security.
You've hit on a core and honestly often underestimated vulnerability. AI systems, just by their nature, rely so heavily on vast amounts of data. For training, validation, live inference, this inherent dependency makes data integrity, data quality, data security not just important, but absolutely paramount for the AI's overall security and reliability.
So bad data means bad AI security.
Essentially, yes. Any adverse change in that underlying data, corruption, unauthorized access, deliberate poisoning, can significantly impact the AI's performance, its accuracy, and its security posture. It's like building a high-performance engine, but forgetting the fuel quality matters just as much.
Right, contaminated fuel engine fails.
Precisely, no matter how well engineered the engine is. And this profound data dependency brings us to the unique elements of AI change management. Managing changes in AI systems is quite different from traditional software.
How so?
Well, in traditional software, a fix is often a discrete patch. For AI, changes are far more interconnected. They can have ripple effects across the entire system. First, consider the durability of AI solutions. AI systems and their security needs evolve incredibly fast, new data, new threats, new research. So solutions must be inherently adaptable, resilient to unknown changes. User-friendly, intuitive, modular design is key so humans can manage, update, retrain them effectively without adding new vulnerabilities, building for continuous evolution.
And the people managing it need special skills.
Oh, absolutely. Second point, skills and competencies. Organizations need to constantly analyze their workforce, identify and develop the necessary AI security skills. Not just traditional cyber expertise, but MELIS security, data science ethics, model governance. It means adapting training for the human element, ensuring people know how to securely interact with, manage, and evolve these systems as they change. It's profoundly about the people keeping pace with the tech.
Okay, and third?
Third, and maybe the most challenging, unknown changes, often called model drift or data drift. AI models can sometimes just produce unexpected outputs or encounter situations not foreseen during training.
Not really a bug.
Not in the traditional sense. It's a fundamental challenge of continuous learning in dynamic, real-world environments. This leads to unknown risks, unpredictable vulnerabilities. Building robust architectures that can anticipate, detect, and gracefully handle such unforeseen changes, maybe by triggering retraining or human review, is crucial.
Designing for resilience against the truly unexpected.
And this complexity ramps up with emergency changes. Oh, definitely. Emergency changes for AI systems are much trickier than for conventional software. A simple code patch might not work. Why? Because of that deep interconnectedness models, data versions, underlying code. Changing one thing can have cascading ripple effects, potentially introducing new, unforeseen vulnerabilities or degrading performance unexpectedly.
So what do you do in an emergency?
Well, the manual highlights two key considerations. One is the critical ability to roll back to an earlier AI model. If a critical issue arises, a severe vulnerability, catastrophic performance drop, you might need to revert to a prior, verified, known good version.
Which means good version control.
Robust version control systems designed specifically for AI models and their associated datasets are essential for quick, reliable rollbacks. The second is the absolute need to implement urgent validation immediately after any emergency change. Rapid, comprehensive validation is crucial to ensure functionality and performance are restored, and crucially that no new issues or vulnerabilities have been introduced.
Checking the fix didn't break something else.
Exactly. Often involves specialized automated tools for quick, robust validation against security benchmarks and performance metrics. Diligence is key. Ultimately, the manual stresses the need for approved, agile change management protocols specifically tailored for AI's unique challenges.
So as we've explored today,
Oh.
from understanding the very layers of AI itself, ML, Gen AI, neural networks, to embedding security throughout its lifecycle with DevSecOps, and then meticulously managing its data dependencies and unique change protocols, we're building this strong, comprehensive foundation for secure AI.
It's a holistic view.
It really is. Yeah. And it's truly about being proactive, isn't it? Designing for resilience, for trustworthiness from the very start, rather than scrambling to react after a problem emerges and maybe causes significant damage. This holistic approach feels like the only way forward. All right, so to wrap up this deep dive into Chapter 3, Part A of the AAISM manual, let's just quickly recap the critical insights we've uncovered today. We've really tried to push past the headlines, explore the fundamental building blocks of AI, deciphering the nuances between machine learning, deep learning, generative AI.
And touching on AGI and super AI.
Right, those future concepts too. And understanding the mechanics of neural networks, the learning types, and key considerations like LLMs, prompts, foundation models. But it wasn't just about understanding what AI is, was it? We took that crucial next step. Unpack the absolutely vital concept of AI security by design.
Weaving it into DevSecOps.
Exactly. How security should be meticulously woven into every single stage planning, coding, testing, deployment operation. And we delved into that critical, often overlooked role of data management and the unique challenges of change protocols for AI systems, highlighting why data integrity, quality, robust change processes are just paramount for resilience and trust.
Couldn't agree more.
So what does this all mean for you listening in? Well, it means that whether you're a developer crafting AI models, a manager overseeing projects, an auditor assessing risks, or maybe just someone fascinated by AI's transformative power, a comprehensive, proactive approach to understanding and securing these systems from the ground up is absolutely paramount.
It really is non-negotiable going forward.
Yeah, recognizing the intricate dependencies, the dynamic nature, the continuous need for vigilance and adaptation.
You know, this raises an important question, I think. Considering this rapid, accelerating evolution of AI and the manual's profound emphasis on integrating security from the earliest design stages, literally baking it into the architectural blueprints, how might the role of the traditional cybersecurity professional need to evolve to truly become an AI security architect in the coming years?
That's a great question.
What new specialized skills beyond general cybersecurity knowledge and what new frameworks will be most critical to master? Especially as AI becomes even more pervasive, fundamentally transforming industries, societies. It's a challenge, sure, but also a huge opportunity that demands foresight, continuous learning, and maybe a real shift in perspective.
That's a powerful thought to leave you with, and a crucial one as we all navigate this new technological frontier. We really invite you to reflect on the concepts we've discussed today. Maybe explore how these principles apply in your own fields, your areas of interest. The world of AI security is dynamic, it's ever-changing, and continuous learning is truly the key to staying ahead. Thank you so much for joining us on this deep dive.
Thank you.
We look forward to exploring more fascinating and complex topics with you next time.